Okay, we are going on to part three, where we're going to talk about heat transfer by radiation. Let me dismiss my image, and we'll uh, continue. Radiation. Radiation is the transfer of energy by electromagnetic waves. Examples: solar energy from the sun, radio waves, and light energy from light bulbs. Certainly, if you have a microwave oven, it warms the food by uh, the radiation agitates the water molecules in the food that you're preparing. But that is certainly um, heat transfer by radiation. Um, so they show the radio waves, they show the infrared waves that come from a fireplace, and light waves. I mean, I'm sure you've been to restaurants where, as they put the food up on a rack for the waiter or waitress to pick up, it's under these infrared lamps to keep it warm. Uh, okay, the surface of Earth loses energy to outer space due mostly to conduction, convection, radiation, or radioactivity. Well, um, the main loss comes through radiation. Radiation is the only possibility owing to the relative vacuum of outer space. The absence of a fluid medium precludes convection to space, and the lack of solid matter in space precludes conduction. So the only uh, uh, available method is through radiation. Okay, which body glows with electromagnetic waves? The sun, the earth, both A and B, or none of the above? Actually, it's both. The sun and the earth. Earth glows in long wavelength radiation, while the sun glows in shorter waves. Um, Radiant energy, uh, it's emitted by all bodies, transferred through space. If you ever are able to look through an infrared camera, you can see that you know people glow because they're radiating heat. If you were to put your look at a cold wall and place your hand on the wall and then remove your hand, looking through an infrared camera, you would still see the imprint of your hand on the wall because you've warmed it up. And so now it's emitting that warmth. The wall is emitting that warmth. So all bodies uh, emit radiant energy. Um, it exists as electromagnetic waves ranging from long radio waves to short wavelengths. And there's a little spectrum here: the radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. And you'll notice that the lower the frequency, um, I mean the lower the frequency, the longer the wavelength. Um, so, uh, and a little aside here, this is not necessary for you to know. I just thought it was interesting. This is if we go back, you can see there's a little section right here that has visible light between infrared and ultraviolet. And you can see that violet is on one side and red is on the other. So infrared, it has a longer wavelength than 700 nanometers, and ultraviolet has a uh, lower wavelength than uh, 400 nanometers. This just I just thought it might be interesting for you to see. Now, note that the wavelength ranges here are approximate. It actually says different people will describe colors differently. Um, so again, this is not for anything. You're not going to be tested on this. There's no homework on this. It was just interesting. Okay. Wavelength of radiation related. It's related to the frequency of vibration of an electromagnetic wave. A low frequency vibration implies a long wavelength waves. Um, A high frequency vibration implies short wavelength waves. Um, okay, emission of radiation energy. Every object above absolute zero radiates. The sun produces solar radiation, including visible light. The earth produces terrestrial radiation in the form of infrared rays. These have frequencies beneath the threshold of our eyes to detect as visible light. Again, if you were to look with an infrared camera, you would probably see the that it was emitting something. Um, okay, the uh, emission of radiant energy uh, continued is frequency of radiation is proportional to the absolute temperature of the source. So here's the this frequency um, relates to a Kelvin temperature of 1600 K. This peak frequency relates to a temperature of 2400 Kelvin. And this one up here, 3200 Kelvin. And here would be the visible light. But so the peak frequency is proportional to the Kelvin temperature. Okay. Okay. Range of temperatures of radiating objects. Room temperature emission is in the infrared. At temperatures above 500 degrees C, object emits red light. Longest waves are visible. At about 600 degrees, object emits yellow light. And at 1500 degrees C, object emits white light, whole range of visible light. When you have white light, you have all the colors there. Um, okay, absorption of radiant energy occurs along with emission of radiant energy. The effects of surface of material on radiant energy, any material that absorbs more than it emits is a net absorber. Any material that emits more than it absorbs is a net emitter. Net absorption or emission is relative to the temperature of surroundings. Now, don't don't think that okay, there are some materials that are only absorbers and there are some that are only emitters. No, that's not true. Whether it's an absorber or an emitter depends on its temperature relative to the temperature of its surrounding. And we'll see a couple of examples of that. Absorption of radiant energy occurs along with emission of radiant energy. Good absorbers are good emitters. Poor absorbers are poor emitters. Example, a radio dish antenna that is a good emitter is also a good receiver. By design, it's meant to do that. Um, a poor transmitter is a poor absorber. But you know, when you have an antenna, you want to be able to receive a signal and transmit the signal, at least if you're in communications. So it has to be both a good absorber and a good emitter. Okay, if a good absorber of radiant energy were a poor emitter, its temperature compared with its surroundings would be lower, higher, unaffected, or none of the above. Well, if it's absorbing radiant energy, but it's not emitting much, it would have a higher temperature. If a good absorber were not also a good emitter, there would be a net absorption of radiant energy, and the temperature of a good absorber would continuously get hotter and hotter. And nature doesn't behave that way. Okay, so it's uh, whether something is an absorber or an emitter depends on the relative temperature of the surrounding environment. Okay, hot pizza placed in snow is a net absorber or a net emitter. Okay, it says hot pizza on snow, it's going to emit because it's hotter. Net energy flow, the frequency is related to the temperature, goes from higher to lower temperature. Since the pizza is hotter than the snow, emission is greater than absorption. So it's a net emitter. Okay, let's see. Which melts faster in sunshine? Dirty snow or clean snow? Uh, Is it dirty snow, clean snow, both of them? Well, if it's dirty snow, that means it has more black, and black tends to be a better absorber, so it's going to be the dirty snow. Dirty snow absorbs more sunlight, whereas clean snow reflects it. It reflects the the sunlight. So the dirty snow is a better absorber. Reflection of radiant energy. This is opposite to absorption of radiant energy. Any surface that reflects very little or no radiant energy looks dark. Examples of dark objects are eye pupils, open ends of pipes in a stack, open doorways, or windows of distant houses in the daytime. Um, I think they show a little example here. The darkness is often due to reflection of light back and forth, many times partially absorbing with each reflection. So you've got the energy coming in, but very little comes out. Good reflectors are poor absorbers. Uh, okay, which is the better statement? A white object readily absorbs visible light. Black object readily absorbs visible light. Black objects do not emit any radiation. White objects do not absorb any radiation. Well, if you have a black car as opposed to a white car, you're going to want to let that black car cool off because black tends to absorb energy, um, absorb visible light. It absorbs a lot of the energy. Uh, the same thing if you wear a black T-shirt or a black shirt on a hot day, you're going to be a lot hotter than if you were to wear a white T-shirt, a white shirt. The reason a black object is black is because it absorbs visible radiation and radiates energy using frequencies that are not visible. All objects at constant temperature absorb and emit radiation at the same rate. The color of an object is a consequence of a difference in frequencies associated with these two phenomena. Okay, and that's the end of part three. The next section, we're going to uh, discuss multiple topics, but we're going to do it all in one video. Okay.